All right, example 4.5, number 2, in relative motion, talking about vectors. This one is, it's easy, it's easier in that we already have kind of our subscripts laid out for us. Honestly, you can pick whatever subscripts you want. We've got a boat, we've got the ground, we've got water. You can call them whatever you want, but this has already been spelled out for us. What's a little more difficult is that we don't exactly have a perfect right triangle right here. So we're going to have to do this in some parts. Okay, so let's spell out, or let's lay out what our various vectors are. Okay, we've got a boat moving through water. Okay, and so the velocity of our boat with respect to the water is going to be 6.1 meters per second. But it's also pointed at a certain angle. All right, at what angle is that? That's 25 degrees upstream. All right, well, if that's upstream right there, and we have our x and y axis, why don't we just call it upstream north, and we can say it's 25 degrees north of east. All right, that's that direction right there. But we also have the stream moving. So the water is moving through the stream, and the stream is moving how, or with respect to what? Well, water moves over the ground, right? And so the water, the velocity of the water, the velocity of the water with respect to the ground is what? Well, it's flowing this way, right? It's flowing due south. So that is, what direction is, where does it say how fast the water is? Oh, okay, 1.4. 1.4 meters per second. Okay, so the water is flowing this way, 1.4 meters per second, and the direction is very important. So if this direction was north, then this direction has to be south. So it's moving at, you might say 90 degrees, south of east or south of west or just south. Okay, straight down, right there. These are our two working vectors. Now, the real question is, are we able to find out the velocity of the boat with respect to the ground? What's the velocity? It says your velocity, but you mean you and the boat. Velocity of the boat with respect to the ground. Can we find that? Well, the first question to ask is, do we have our subscripts in the right order? Remember, velocity of 1 to 2 plus the velocity of 2 to 3 equals velocity of 1 to 3. Can we just add these up and get this one right here? Velocity of the boat to the water plus the velocity of the water to the ground. That looks pretty good, right? 1 to 2 and 2 to 3. They should be in the right order so that we can get the velocity of the boat to the ground. So for part A right here, we're just finding your velocity with respect to the ground. And it's also going, that's this right here, all right? Because you're pointing upstream, but the water is moving you downstream, so you're going to go downstream a little further at some angle. That's for us to find out in part A of this problem. All right, so let's see right here. I'm going to move to another slide where it's more blank. 6.1 and 1.4. Okay, I'll have to remember that because I don't want to keep flipping back and forth. All right, next slide. So let's, okay, example 4.52, part B. If you were with us for part A, we talked about how if a boat is kind of angling itself upstream and then the water from the stream carries it downstream, what will the final velocity of the boat be with respect to the ground? Here what we're doing is going to be a little more, not a little more complex, but we need to set some things in motion first. I think we said before that the boat is trying to travel this way through the water, but the water is moving downstream like that. So this right here would be the final direction of the boat, okay? But in part B, what part B states is, so this was A right here. Part B says, all right, well, what is the direction of the boat if we want it to go straight across the stream? So what I suggest we do is we actually draw this out and sort of illustrate what we want to have happen. So here what we have are the two sides of the stream. Okay, so on either side we've got trees and all kinds of crazy grass right here on the side. So this is the ground. All right, and in the middle we've got water flowing. Okay, and it's flowing the same direction that it previously was. So we can state that right off the bat that the velocity of the water to the ground is still going to be the same as it previously was. That's 1.4 meters per second at 90 degrees south, all right, due south. But what we want to have happen is this. So here's our boat right here, all right. It's a pretty terrible boat. Try that again. It's supposed to be like a rowboat or something, but a little better. Okay. What we want to have happen is this. Even though the boat is aiming itself upstream and the stream is carrying it downstream, we want the boat to be carried straight across. That is the resultant vector to go straight across the stream. That's what it says in part B. All right. What direction is required for the boat to go straight across the stream right there? So what we've done is we've created a right angle triangle right there. All right. The velocity of the boat with respect to the ground we don't know, but it's something meters per second at 0 degrees north of east, right? That's going to be really important to us right there to find the angle at which the boat needs to be angled upstream. So, what do we do? Well, since we have a right triangle, we can assume some things now, because we have forced, I should draw that in there. We have forced our boat to go straight across the stream. The question really is, what is this angle right here? That's really what part B is asking. Because we know this velocity. We know the velocity of the boat through the water because it hasn't changed from before. That is still velocity of the boat to the water. Oops, I keep writing the water. I'm writing G. What's going on with that? Boat to the water is still going to be 6.1 meters per second. Now, we don't know. That's an and, or that's an at sign right there, or it's supposed to be. We don't know the direction, and down here we don't know the velocity that it's going to be doing through the water. That's going to be part C actually. But we can find the direction. We can find this angle because if we draw this out, that vector plus that vector gives us this right here. What we have is a hypotenuse value, right? 6.1, and we have one of the sides of the triangle, this right here is 1.4. We should be able to find this angle pretty easily because we have an opposite and we have a hypotenuse right there. What's the trig function for that? Well, the sine of some angle, I'm going to write that in red. Sine of some angle theta equals opposite over hypotenuse, right? So if the sine of the angle is opposite of hypotenuse, then that means the angle itself must be the inverse sine of the opposite over the hypotenuse. All right, again, we can do this. We're not actually doing the vector addition through components. We're just using trig right here because even though we don't know this direction, we do know the magnitude and we know this magnitude. And if we assume it's a right triangle, we can apply trig functions here. So let's just plug in our values then. Inverse sine of what over what? Well, the opposite is 1.4 and the hypotenuse is 6.1. What angle do we have right there? 1.4 over 6.1. 13 degrees. All right. What is that north of east, right? That's going to be our answer for part B. Because B is really asking us, what's the direction? We're told that the magnitude of the boat moving through the water is the same, and the water's magnitude and direction hasn't changed. So we want to turn this into a right triangle, assuming the boat is going to go straight across the river. And that helps us to find our angle right there, 13 degrees north of east. The last part should actually be fairly simple as well, because, let's do this in black. What we're asked is, what is the velocity of the boat with respect to the ground? All right, we know the direction is, well, straight across the river, so we can assume the direction is 0 degrees north of east, or just 0 degrees due east. But what is that velocity of the boat to the ground right there? Well, that should be pretty easy too, because we know the velocity, we know the magnitude of the vectors that add up to that that right triangle right there. Again, this is a right triangle. So if the velocity of the boat to the water, which is the hypotenuse, squared, equals the velocity of the water to the ground, squared, plus the velocity of the boat to the ground, squared, right? Leg, hypotenuse, then we should be able to figure out the velocity of the boat to the ground. All right, so the velocity of the boat to the ground, let's just, well, move this guy over to that side, and then we'll take the square root, right? So it's going to be, I'm just going to write this all in black now. Velocity of the boat to the water, squared, minus the velocity of the water to the ground, squared. All right, so because we moved that over to that side, then we want to get rid of this square right here, so we take the square root of both sides. And that will give us our velocity of the boat to the ground. That is going straight across the water right there. All right, so let's plug our values in and see what we get. Velocity of the boat to the water, that is 6.1 meters per second. Or, well, I'm just going to put 6.1. Leave the units out for now. 6.1 squared minus velocity of the water to the ground minus 1.4 squared. Make sure you square it first and then subtract it from the 6.1 squared. That's going to give us our velocity of the boat to the ground. 6.1 squared minus the quantity 1.4 squared. All right, 35 point something to the half power. That is the square root. 5.9 meters per second. That's the speed, or you might say the velocity of the boat with respect to the ground. This is the direction right here. And, I'm sorry, this is the direction that the boat should be pointing. But if the boat is going to go straight across the river, it's going to go straight across it due east at this velocity right here. So this velocity and this direction are not related to each other. This is the direction that the boat is pointing. This is the velocity that it really finally takes as the boat is moving through the water, which itself is moving with respect to the ground. So I hope that helps. The important thing to keep in mind is to make sure you have your subscripts straight right here, so that when we add vectors together, relative vectors together, we don't get our vectors backwards. So thanks for watching, and I'll see you in the next one.